Welcome back. So in the final two parts, part 4 and part 5, I will focus on specific properties of the Ising model. And in this part, I concentrate on the high temperature region. Okay, so this is theorem 4, which is proved in this part 4, and it says that there is a constant beta h, and actually it's determined by this, such that for any beta less than beta h, spontaneous magnetization is vanishing. Okay, and I like to stress that this constant, the choice of constant, is not meant to be optimal. Okay, this does not give the exact value of the transition point. Okay, this is chosen for technical reason and it can be improved. But anyway, so this is what we are going to prove. Okay, so as before, I will first state the basic lemma, which contains the essence, and by assuming this lemma, I will prove theorem 4. Then I will turn to concentrate on the proof of this lemma. Okay, so what does this lemma say? Well, so if beta satisfies this, so actually it means that beta is in this range, then for any non-negative h and any site u and any system size L, this quantity, this is the expectation value of sigma u, the spin at site u, in the periodic boundary condition in the system size L, inverse temperature beta, and magnetic field H. And this expectation value is upper bounded by this quantity. Okay. Now, so here you have beta and here you have beta h, and you can of course upper bound this hyperbolic tangent by beta h. So we have this upper bound. Okay, so this will be useful. Okay, so I'm going to prove this theorem now, assuming this. So first of all, I note that, and let me say that, okay, here I use periodic boundary condition, but I noticed that we can do the same thing by only using free boundary condition. So I think somewhere in part 2, I said that we need all three boundary condition, free, periodic, and plus. But actually, it was wrong. It was enough to consider, for example, free boundary condition and plus boundary condition. But anyway, the periodic boundary conditions are something very standard, so I think it's worth considering it here. Okay, so I will first note that free energy density for finite system size and in the periodic boundary condition satisfies this inequality here. And this is actually simple. This comes from two facts. First of all, this f is a concave function of h. Okay, and also it is symmetric. It is an even function. So if you want to draw a graph of a concave function which is also even, then what you can do is simply like this, and here it is h equals 0. So it takes maximum at h equals 0. So this is what it says. Okay, so you can prove this in any way, but for example, this is a compact proof. So first of all, from the definition of concavity, you draw this thing, and this is above this. Please go back to part 1. Anyway, from the definition of concavity, you know that this is valid. Okay, and then we know that this is an even function, and then these guys are equal, so you know this is equal to this. So this is this inequality. Okay, and of course we have not used this. Okay, next. Now I suppose that h is strictly positive and beta is in this region. Okay. Now if I differentiate f with respect to h, and then this is again standard, we get the expectation value of the magnetization density, and here minus sign. And now since this guy satisfy this inequality, I will plug this inequality in. And here are a bunch of u's, but they are actually all the same, and they satisfy the same inequality. So you simply it is enough. It means that summing all this up is the same as you multiplying this by L squared, but you divide it by L squared. Okay, so what you get is simply this. Okay, now with this, consider the same quantity as before, this difference, and then this is this is written in this way. You differentiate and integrate. Okay. Now for this derivative, you can use this lower bound, so it's lower bounded like this, and then you can simply easily integrate this to get this. Okay. So since h is strictly positive, you can divide this thing by h to get, first of all, it's less than equal to 0 because of this. Okay. And from here, you divided this by h and you get this. Now, at this stage, we let L go to infinity. Okay. And in the and we already know that this quantity has a nice infinite volume limit, the thermodynamic limit. So we get this thing. Okay. And these guys depends on the choice of boundary condition, and they are for the periodic boundary conditions. But of course, as we proved in the previous part, this infinite volume quantity does not depend on the boundary condition. Okay. So anyway, from this we get this. So nothing else depends on L. So we get this, and then finally we let H go to 0 from above. Okay. And this guy, by definition, converges to the right derivative, and this is 0, and this converges to 0. So this means that the right derivative is 0. And this proves that the spontaneous magnetization is vanishing. Okay, so that's the end of the proof of theorem 4. So of course, our main job in this part is to prove this lemma. Okay. Okay, so let me let me start proving this lemma. So the basic strategy of the proof is to use a stochastic geometric representation of this expectation value. So probably you don't get any idea. So let me just show you the final part of the proof. In the final part of the proof, we will reach this upper bound for this expectation value. Okay. I didn't write it, but this is for oops. This is for periodic boundary condition and system size L. Okay. And now, what does this say? Well, this inequality says that this expectation value is upper bounded by this thing. What is this? Here I have sum over n, which runs from 0 to infinity, and here I have summation over all n-step random walks that start from u. Okay, and here is a factor a to the n times b, and a is actually hyperbolic tangent beta, and b is hyperbolic tangent beta h. Okay, and this is a stochastic geometric upper bound, and in the sense that we are summing over all different patterns of random walks. So they are stochastic geometric quantities. Okay, and so by a random walk, I mean really a random walk. So you start from u and go step by step, and you can never use same bonds twice, and just go beep, 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 and stop somewhere. And so this is 6. In this case, n equals 6. 1, 2, 3, 4, 5, 6 steps. Okay, and then the walk terminates here, and here you get corresponding factor weight here, and the weight counts the number of these walks, and finally it takes this factor. And this factor a, hyperbolic tangent beta, sort of represent the interaction term. So here you start and you make use of interaction and come here, come here, come here, come here, and this factor b represents, of course, the effect of the external magnetic field. So you start from here and you walk, and then you pick up the effect from magnetic field, and you do the same thing here. This is an 18-step walk, and here you pick up the effect of magnetic field, and so on. So we sum over all such possible random walks, okay, starting from 0. 0 means you are just here and pick up this. Okay, and we will show. So in this proof, we show that this is valid, and then the final step is to show that this converges and gives us the desired upper bound. Okay, so that this is the final goal and we need 11 pages. But let me go back and start proving this. And the basic reference I understand of this kind of method goes back to Professor Michael Fisher's paper in 1967. This is Professor Fisher. He's one of the masters in statistical physics, but unfortunately he passed away rather recently. And he has a guitar, but he was very good at guitar. I understand he was almost a professional player and composer of Spanish guitar. And actually, I had a chance to listen to his guitar. That was nice. Okay, so anyway, so let's go back to the proof. So in this part, I only used periodic boundary condition. So let me just abbreviate many symbols. So I won't write L here, so I won't write this. So if I write B, it means this and this and this and everything. Okay, and probably more. But anyway, I will just abbreviate this periodic because I'm use periodic boundary condition. I always fix L. Okay, and now here comes the basic observation, the starting point of everything, and I introduce this AB factor here. Okay, so this is the both. So this is Hamiltonian. So I cannot abbreviate H because this varies. Okay, so this is my Hamiltonian in periodic boundary condition, and then this is the Boltzmann factor. And first of all, this is of course e to the beta sum plus beta h sum. So, but when you have summation over exponential, you can bring it down, and you can write it in this way as a product. So this is written as a product over all bonds in B, which is this, of this factor times the product over all sides of this factor. Okay. Now I claim that this can be written in this way, but let me explain why, first of all. So I first claim that for any tau, which takes plus or minus 1, and for any alpha, this e to the alpha tau is written like this. Hyperbolic cosine alpha plus tau times hyperbolic sine alpha. Why is this? Well, this is actually very simple because tau is either plus or minus. So first, suppose that tau is 1, and then this is e to the alpha, and this becomes hyperbolic cosine plus hyperbolic sine. But by definition, this is of course equal to this. Okay, and then the other case is suppose that this is minus. So this becomes e to the minus alpha, and this becomes this. But again, this is clear from the definition. Okay, so this looks fancy, but this is just a trivial identity. Almost comes from the definition, and then you just rewrite it this way: hyperbolic cosine times 1 plus tau times hyperbolic tangent alpha. Okay, and then I just use this. I just use this identity here and here. Oh, because now in this case sigma is plus minus 1. So here I regard sigma as tau. Here I regard sigma as tau. Okay, to get this formula here. So I put hyperbolic cosine here, and this is okay. Of course, these are the main things. And here, so that's why I got this hyperbolic tangent factors. And as I already show you, these factors A and B play essential role in the proof. Okay, and this part doesn't play any basic role, so it's just here. And of course, as I said before, whenever I have a finite set, and then this denotes a number of elements in this set. Okay, so this is simply the number of bonds. So I think it is a 2 times L squared or something more. But and this is just the number of sides. This is L squared. But we don't use this. Okay. All right, so this is the basic starting point. Is this okay? So now I concentrate on this factor here. Okay, now we have this factor here. I have product over all bonds, all possible bonds in this lattice of this quantity here. And first of all, I want to expand this. Okay, so probably it's better to look at an example. So we are focusing on square lattice, but suppose that this is our lattice. It only has 3 sides and 3 bonds. Okay, so in this case, this is a product over all bonds. So we have product of these 3 things. and you want to expand this as usual. So by expansion means that for each of these things, we choose whether we use this thing or this thing. So for this thing, we decide whether we should pick this one or pick this one. Okay. So there are two choices for each of them. So there are 2 to the 3 choices, and I think we have 1, 2, 3, 4, 5, 6, 7, 8 terms. Okay, so that is the expansion. And so the first term in the expansion is of course obtained by picking all 1 here, and you get 1. Okay, and here I draw something here. I just drew a triangle. And here, okay, next thing, then here, okay, let me pick this here, and this here, and this here, and you get this. In this case, so I picked this term with factor A on bond 1, 2. So I draw this. So here I draw something blue, thick blue on this bond. And the same thing. This is obtained by picking 1 here, this factor A here, and 1 here. You get this. So this diagram, this thing too. Okay, let's look at this thing. Here I picked this, this, and this. So in this case, I put these bonds here and here, right? And so this you get this a little bit complicated expansion here. And here, for example, I pick this, this, this. So I get a cubed and this thing, and the diagrammatically this. But you have seen it is rather clear from this procedure or this picture that now this is the expansion is the same as sort of considering all possible subsets of bonds. Okay, so you can rearrange, you can write this expansion in this form. Here the summation is over all subsets of this set of bonds P. And of course subset includes, this is in this case this is the empty set. Okay, so this includes the empty set, and in this case B is B itself. Okay, so but anyway this is the summation. So I think this is clear from this example. So here you sum over all possible subsets, and here you have this factor like A or A squared, A cubed. Again, this denotes the number of bonds in this subset B. And here you have this product. Okay, but now you can rewrite this in a simpler manner because first of all we rearrange this part like this. So what is this? Well, NB of U is denote the number of bonds in B, the subset B, that contains U. Okay, so this is an example. So suppose that these blue things denote this B. Okay, and then for each site you count the number of bonds which is contained, which contains this site. So as for here, there's no bonds. I'm sorry, so it's 0. In this case, it has only there's one bond, one bond. Here, this guy has 3 bonds, this guy has 2 bonds, and so on. Okay, and then you can, of course, this means that how many times sigma u appears in this product. Okay, so you can rewrite this in this way. Okay, and furthermore, since sigma is either plus or minus, sigma squared or sigma, I mean, if it has even power, it is the same as nothing. I mean, sigma squared is 1. Okay, all these things are 1. So the only thing you have to we have to care is when n is odd. Okay, if n is odd, again, then it's the same as this. So the only thing we have to care is the parity of this NBU. Okay, and we should only look at the sites at which this NBU is odd. Okay, so I define this dB, del B or whatever. This is this has a connotation that this is a boundary of this set B. And anyway, so for this dB, the boundary of B is defined as a set of sites in which NBU is odd. Okay, and then this is, of course, this written in this way. I think this denotes the dB for this B. Okay, so I just picked up all sites with odd B, odd NBU. I think this is correct. So I can rewrite this in this way. So this thing is expanded in this way. Okay, and so here's an example here. So this is this expression corresponds to this one. But if you here you see that we have sigma 2 squared, so it's the same as 1. So we have this. So this corresponds to this expression. Oh, in here it's 1. It's 1. Okay, because in this case, all sites contain 2 bonds. So dB is empty in this case, so it only has 1. Okay, good. So okay, so now we have this expression. Okay, and then we will derive a stochastic geometric representation for the partition function with 0 magnetic field. Okay, and now here is Z, and this is the definition. The magnetic field is 0, and then let me go back. So this is the standard expression, but if when magnetic field is 0, you don't have to consider this. You don't have to consider this. So we only have this hyperbolic cosine and this thing. Okay, and as for this thing, we discussed this expansion. Okay, this expansion. So we plug this in. So we have this hyperbolic cosine, and this is the expansion that we discussed in page 4. Okay, and here we have this summation over all possible spin configurations. Okay, now, but I would say that now after this expansion, it's quite easy to take this sum. This is interesting. First of all, in this expression, it is miserably difficult to take this summation. Of course, this is very non-trivial problem. Okay, but we did this expansion, and after this expansion, the sigma dependence comes only here. Of course, this is a very complicated expansion, so there's no free lunch. Okay, so this sum is very hard to take, so we did this expansion, which is very, very complicated, and then we can easily take this summation. And why? Well, this is almost trivial. So if you sum over sigma plus and minus, and if you take the sum of this thing, and then this is 1 minus 1, and you get 0, and in this case it's 1 plus 1, it's 2. Okay, so you want to sum this up, but this is basically the same as summing each u plus summing up over each sigma u, which it takes value plus minus. Okay, so this can be sort of composed into the product of sums. Probably if you understand this immediately, that's okay. If you don't understand this, I suggest you to write down very simple example with like 3 sides, and I think you will understand. Okay. So anyway, what you will find is that this summation breaks into products. So in this case, we have this. So this breaks into this product of u in dB, and in this case, you sum over this sigma u plus minus 1, this thing. Okay, this is inside here, and in this case, this is a remainder. This is all sites which is not in dB, and in this case, we don't have sigma, so we sum over 1. So here, from here, you get 2, and from here, you get, of course, 0. So if you get 0 here, the answer is 0. Okay, so this is very simple. If dB is del B, whatever, if the boundary is non-empty, then the answer is 0. Whenever, okay, when the only case where you get non-zero answer is when this del B, the boundary is empty. And in this case, we don't have this, and we have 2 here, and we just have everything, so we get 2 to the lambda. Again, this is the number of sites, total number of sites. Okay, so we are done with this summation. Very interesting. And we get this totally different expression, but exact rigorous expression of the partition function. Okay, so what is this? Well, from here we have 2 to the lambda, we have, but these are just trivial factors. Okay, you know what they are. And this is a non-trivial part. We have summation over all subsets of B, but with this condition. So this represent a condition for the summation. This is we sum over all possible subsets, but with this condition. This means that this has no boundaries. So this is one example of B, subset B without boundary. And in this case, if you recall the definition of dB, for any site, the number of bonds in B that that includes a site is even. So in this case it's 0, in this case it's 2, in this case it's 2, in this case it's 4. So as you see, such a B satisfying this condition is it looks like this, and it's a collection of loops, closed loops. So there's nothing like this kind of end points. You always has closed loop. Then it can be, of course, very much complicated, but anyway, you get this kind of thing. So interestingly, this is a very complicated quantity. This is sum over all possible spin configurations. Here, instead of sum over all spin configurations, we get the sum over all these geometric objects that consists of loops, closed loops. Okay, so this is why we call this stochastic geometric representation. This is a kind of statistical mechanics for geometric objects. Okay, and okay, so this is a weight. Right, so this is an exact expression, but we have to do further more because we want to include magnetic field. Okay, so again, let me go back. So this is the original expression for the Boltzmann factor, and we have dealt with this. We consider this term. So when we have magnetic field, we also have to consider this thing. So okay, now we will go. We will look at similar stochastic geometric representation of beta h when h is non-zero. And then magnetic field term yields this thing, but I think this is clear. In this case, we get this expansion. Now, in this case, S is summed over all subsets of lambda. Okay, so these are now sets of sites. And this is a stochastic. This is a weight, and here you have this. So now, if we plug everything back into the formula of z to the beta h, we have these factor, and of course we have this in front, and we have sum over all possible subsets of B, and sum over all possible subsets of lambda, and this and this. Okay, and this is here's the factor. Now again, I want to take this summation. So you can bring, of course, this summation here, and you consider this. But again, now I think it's clear. So here we have sigma. So these are sigmas coming from dB. These are sigmas coming from S. Okay, and we want to sum over all possible spin configuration, and we know the answer. I mean, in order to get non-zero thing, we have to have the situation that this is exactly 1. Otherwise, what if any spin variable remains, then it gives you 0 after the summation. Okay, so the condition that this is equal to 1 is clear. Since sigma squared is 1, this is realized. This is non-zero. No, this is equal to 1 only when dB, the boundary of B, and S are the same, are identical. Okay, so in this case, we get slightly different stochastic geometric representation, which is this. So we have this factor here, and we have 2 to the lambda and this thing, so we can put them together to have this factor. But anyway, these are trivial, and we don't have to care about this. And this is the essential part. We have now sum over all possible subsets of this curly B, and now there's no restriction. You can sum over all subsets, and this is a corresponding factor that comes from here. Okay, since S must be equal to dB, so we don't have to sum over S. So instead of summing over S, we just forget about this, and we replace this S by dB. Okay, so this is again the exact formula for Z, and of course, I mean, this is not at all easy to evaluate, but this looks totally different from the original thing. So here's an example of a term that appears in this expansion. In this case, you don't have to care about forming a loop. Okay, so anything is okay, but these red points denote the elements of dB in which the number of bonds coming from this site is odd. Okay, so for all these red points, you have to include this factor that comes from magnetic field. Okay, so as I said in the introductory part, this A factor sort of represent the interaction mediated by this sigma interaction, and this represent the effect of external magnetic field. Okay, so is this clear? This part is not short, so please pause and think about and rethink and. Okay, so now I want to go into this a stochastic geometric representation of the desired quantity, this expectation value. Okay, this is basically the same but slightly more non-trivial. Okay, and here I will fix any site in the lattice and consider this quantity. Okay, so of course this is the quantity we want to treat, and this is of course defined by this thing divided by z. Okay, but so here I want to consider this unnormalized expectation value, which is easier to treat for the moment. So z times sigma expectation value is written in this way. Here's the same Boltzmann factor. Then we can repeat the same game, right? Because for here, we know that this is expanded. Well, probably I don't have to say this, but this part could be expanded in this way, right? Without the summation. Okay, yeah, this is just the expansion of the Boltzmann factor. Okay, so exactly the same expansion. So without this is this is the expansion of the Boltzmann factor, this thing. Okay, and now but we want to have this, so we added this, and then we will sum over this, and of course you can write it here, but we already know that all these guys do not depend on the spin configuration, so the only thing you have to do is this. Okay, so now we think about evaluating this summation, and of course it's the same. I mean, this summation is either 0 or 2 to the lambda. Okay, it's the same. But now the condition of giving 2 to the lambda thing, non-zero thing, is slightly different because now we have product of these three things. Okay, and we have to be careful that this will the product is exactly 1. So we want to know the condition that this is 1. So first of all, we have to be careful about treatment of this u. In previous cases we had this some okay, this is exactly the same as the before, but here I say u v, but now u is a fixed site, and so I used v here and w here, but anyway it's the same thing. But anyway, here v and w are chosen from db and s, and they can be these guys will change, okay, because of the summation. But here sigma u is always there. Sigma u is always there, so we have to be very careful about the treatment of this sigma u. And so if you examine the condition that this is equal to 1, you will find that we have two distinct cases. Okay, in first case, so anyway, here's sigma u. So there must be one more sigma u from here, right? And then this will give you 1. And we need one more u and exactly one more, because you get 2 sigma u from here, then we have sigma u cubed, which gives you sigma u, and the summation will become 0. Okay, so we need 1 sigma u from here. So the choice is whether we get u sigma u from here, that's case 1, or sigma u from here, that's case 2. Okay, so in the first case, u belongs to S. And you should not belong to db. Okay? And furthermore, and so this condition takes care of this. And of course, but we want the whole thing to be 1. So that we of course need an extra condition, and db must be equal to S, but 1 of S is already used to compensate to kill this sigma u. So this is a set obtained by taking away u from S. So db should be equal to this. Okay. Now suppose in the second case, suppose that in this second case u is here. And in this case, so u is in the boundary of B, so u should not be in S. And in this case, similarly, this set obtained by taking away u from dB, it should be equal to S in order for everything to be 1. Okay, so anyway, this is the condition. And then again, this thing is exactly written like this. Okay, so here we have this standard factor. These are summation over b and s, and we have to have condition 1 or 2. Okay, this is nothing very difficult, but it's a little bit more complicated than before. Now, here comes the non-trivial part. We shall construct or extract random walks from the sets B and S satisfying the condition 1 or 2. Okay, and I roughly introduced what random walk is, but let me state it more carefully. So by an n-step random walk W, I mean this sequence of sites W0, W1, Wn, such that each pair Wj, Wj plus 1 is an element of bond. It's a bond. Okay, it belongs to this set of bonds. So it's as I said, it goes like this. So where in each step you pick your bond and goes like this. Okay. Now, so suppose that case 1. So suppose that S, B, and S that satisfies this condition 1 is given. So these blue things denote the bonds in B, and this pink dots denotes the sites in S. Okay, so this is an example, and in this case, U condition says that U is in S. So yeah, so U is on this pink site, and it's not on DB. Of course, yeah, it's not on DB. It does not touch any site here. And in this case, no, this is also satisfied. And in this case, what is our random walk? Well, it's very simple. It doesn't do anything. It's a zero-step walk. It's a zero-step walk, and omega 0 is equal to U. And so this W or omega, so this walk itself is simply consists of one site. So it's a walk which still has not started walking. So it's here. Okay. So we pick this thing anyway. And then I define new sets B prime and S prime from here by taking away this random walk. And in this case, it's quite simple. So this random walk consists of a single point. So I just take away this single site from S. Okay, and the remaining is denoted as S prime. So it's here. Okay? And the B doesn't change. So here B prime is the same as B. So the same thing. And S prime is almost this one, but it doesn't contain this. Okay, here. And I claim, this is very essential, I claim that after this construction, we have this condition. dB prime is equal to S prime. Well, I think this is clear. So to begin with, dB and S satisfy this thing. But now this is precisely S prime, and B is equal to B prime. So this leads to this. And why is this interesting? I think you understand, but this is precisely the condition that we found for this representation of partition function. Okay, so in this case, in partition function case, this bare B and S we had in the beginning satisfied this. And here, in this case, the original thing does not satisfy the same relation. It satisfies this modified relation. But after taking away this random walk, this B prime and S prime satisfies this condition, which is the same as the condition for the partition function. Okay, now here's more non-trivial case. So let's consider case 2, where U does not belong to S, and U belongs to one of these boundaries of B. Okay, and the B and S satisfies this. Now in this case, it's more non-trivial. So as this suggests, U belongs to this kind of path. U is the edge of this kind of path contained in B, and so you start from U and just follow this thing which is in B, and then you will finally reach a point where it ends. And here you have S. Okay. So you naturally pick up a walk that starts from U and ends in one site which belongs to DB. Okay, so this belongs to dB. This guy belongs to dB. So we declare that this is a random walk. This is a random walk that is constructed from this B and S. Did I say this? Again, this is, of course, these blue things denote elements of B, and these pink things are S. Okay. And this belongs to the boundary of dB, but it doesn't belong to S, right? So it doesn't have any pink here. Okay. And in this case, this is our random walk. So this does not fully define, but yes, probably it does. Oh, it does. Yes, it does define. So this random walk is chosen so that the initial point, if W0, is equal to U, and each thing belongs not only to this curly B, but belongs to B. And finally, it ends on a site in S. Okay, so this is our construction. Okay, now after this, we again remove this random walk to get new B prime and S prime. Okay, now in this case, this is clear. So we use this portion of B to construct our random walk. So I just take away random walk from B to get this. These are sets of B prime, B prime. Okay, and as for S prime, well, we don't have to do almost anything, but this guy here is used as an endpoint, as the endpoint of the random walk. So we also delete this thing. And again, you find that this relation leads to this. In this case, yes, in this case, you have to be slightly more careful about this, but I think from this picture, it's clear that this is true. Okay. So in both the cases, we could construct a random walk. We can always construct. So whenever 1 or 2 is valid, then we can always construct a random walk that starts from U and ends at some point in S. In this case, it ended at U, but here in general, it ends somewhere else on the site which belongs to S. Okay? And you can always construct such a random walk, and after construction, we just remove this random walk from the configuration to get new B prime and S prime, and they satisfy this condition. Okay. Now, probably you ask a question whether this construction of random walk is unique, and the answer is no. And this is an obvious example. So for example, if this is U and if this is a portion of B, then there are in this case 3 possible random walks you can construct. But this is not a problem because we want to prove an upper bound. So this will give us an overcounting, but we don't care about this. Okay, now we are very close to the end. So what? This is the representation we obtained for this unnormalized correlation function. Okay, so this is already reset. And then from B and S satisfying 1 or 2, we can always extract a random walk. So we do this random walk construction, and we extracted a random walk which has n steps. Okay, so now I will sum over all random walks that can be constructed, that was constructed. So I first sum over the number of steps. So and it starts from 0 step, which doesn't do anything, to something else. But of course it never reaches infinity because we're on the same in the finite system. So this can be never infinite. I mean, it's at most this. But anyway, we are dealing with upper bound, so we don't care. We just write this. And here is the sum over W, the random walk that start from U, and it has n steps. Okay. And here I have an extra factor that we take away, because here we are summing over B prime and S prime and just taking into account this factor here. Okay. So here, originally we had this factor here. So originally we have this factor here. Okay, so this contains everything, but now B is split into omega and B prime. Okay, and so on. So in S is split into the part into a single site that contains a random walk and S prime. Okay, so if I well, probably this is enough. Okay, so these B and S contain everything. So if you extract random walk out of here, then of course you need to extract some extra factor from here. Okay. Oh yeah, I think this is clear. B consists of B prime and random walk. Okay, and random walk contains just exactly n sites. Okay, so this becomes this and this, and this is much more easy, and this becomes this and this. Okay, random walk always takes a single site from S. Okay, good. So here we have this factor, and what is this huge sum? Well, this is summed over all possible B prime and S prime. Okay, and so of course B prime, so oops, these are B prime and S prime here, and they are of course subsets of B curly B and subsets of lattice lambda, and as I stressed, they satisfy this condition. And also, they are remainder of this this surgery of taking away random walk. So this guy can, so here we had random walk and we took away this. So this remaining thing can never enter this region where we had random walk. Okay. So here we have this condition. This ensures that B does not intersect with omega, and S prime does not intersect with here. Okay, so these are conditions. Okay, so we get this, and this is upper bound because we are over counting random walks. Like here we are counting the same thing, I think 3 times, but we don't care. We have everything is positive, so we don't care about this. Now, but this is a still very much complicated sum with this strange condition here. Now, what happens if we forget about this condition? Oh, but important thing that we never forget about this condition. But we forget about this condition. So this reminded us that these are the remaining thing after we removed the random walk, but we forget about this condition. Okay, then this summation becomes like this. And of course, then if we forget about these conditions, we are summing over extra subsets, okay? Subsets which were not there. But since these guys are always positive, this simply overcounts thing, and we get an upper bound. So here is an upper bound, except rigorous upper bound. We just forgot about this, and then we have this summation with this condition. But we have seen this before, right? We have seen this before. This is page 6, number 4. So let me show page 6. Page 6, number 4 is this summation. It's this stochastic geometric representation for ZBH. So we had very similar sum, but we had this condition that dB must be equal to S, and we got this stochastic geometric representation. So where were we? Yes. So we got this. So this is exactly the same as what we had for partition function. So this part and this part exactly gives the partition function. Okay, so we get this inequality comes here. So we see that this whole thing by by forgetting about this condition is upper bounded by z. All these things became z times this part. This is a very good news. So, I mean, once this business was a little bit complicated, but now it's very clear. We have z times sigma. So this is a desired expectation value, and we have z times this summation. And but then now you see that it's close to the goal because you have seen page 11. So page 11 is the next page. Okay, so now you can simply divide this by z to get this is this it? Yes, this upper bound here. Okay, and here you have this is the expectation value we want to upper bound, and as I explained before, here we have sum over all random walks. We first sum over all the number of steps, and here I just sum over all possible n step walks that start from u. They look like this, they look like this. And the factor here, A, is hyperbolic tangent beta. As I said before, this sort of represents the interaction, the effect of interaction, and this B, of course, represents the effect of external magnetic field. Okay, so the remaining task is to estimate this summation. Okay, but it's not difficult. Okay, so this is the final page. So this is what we have seen, and this is written in this way, where this Wn is the number, the total number of n-step walks that start from U. Okay, and yes, so well then yes, this is clear. So you only have to sum this thing. And I claim that this W is up. Oh, okay, it's not an easy task to evaluate this Wn exactly. It's a difficult problem, but it's kind of easy to prove reasonable upper bound for Wn, and it's given by this. Okay, it's 4 times 3 to the power n minus 1. How do you prove this? Well, first of all, okay, when zero step, the number of possible zero-step walk is 1. Okay, and in this case, this is, if you plug this 1 here, it's 4/3, 4/3, so it's okay. But anyway, that's trivial case. And okay, so let's think about the first step. So you are here and you want to construct a random walk, n-step random walk. When n equal 1, you can go here, you can go here, you can go here, you can go here. There are 4 choices. Or actually, this is an exact number. W1 equals 4. Okay? So there are 4 possible random walks. And okay, so suppose that you kept going on and you're here. And then what is your choice for the next step? Well, you cannot go back. You cannot use the same bonds twice. So your choice is from these 3 things. So there are 3 choices. And I say that there are at most 3 choices. So in some case, if you go like this and this, if you come back here, then your choice is, I think, only 1 here, because you cannot use the same bonds twice. But anyway, it's just clear that at each step, from the second to the nth step, your choice is at most 3. Is this correct? Or nth step? Okay, yes. So this is upper bounded by like this. Okay, 4 times this, 3. And then the rest is too easy. You just substitute this upper bound here, you get this. So this is written like this. So 3a to the power n, and this infinite sum is easy to evaluate, and you get this. And if you recall this a and b, you find this upper bound, which we wanted to prove. Okay, so I believe that this was not a short part, but we have finally proved this lemma. Okay, and with this lemma, we could easily prove this theorem 4, which says that for high temperature region, oh, now you understand why we had this. Okay, so this factor 3 came from this the number of choices at each step. We said that we have at most 3 choices, so we have this condition. Okay, also this condition is precisely the condition that this infinite sum converges, right? Okay, so did I say this? Well, yeah, probably it was clear from the context. So this was the condition necessary for this infinite sum we evaluated finally to converge. So I show this again. Yes. Yes. So here, yes. Of course, it was clear that in order to sum this up, we needed the condition that 3a is less than 1. Okay. Of course, with this condition, we have this and we have this. I'm sorry. So I was here on this first page. Whoops. Okay, so I was here. So that's why we had this condition. And under this condition, we were able to prove this upper bound, and which means that this spontaneous magnetization is 0 in high temperature. So the remaining important task is now to go to low temperature region, where we use another different stochastic geometric representation, and we shall prove that this spontaneous magnetization, the same spontaneous magnetization, becomes non-zero. That will be the topic of part 5. Okay, so that's all for part 4. Thank you very much for watching.